So thank you so much for coming on Saturday. I'm really sorry to schedule it on Saturday, but we did not had any slot available. So let me just share the file. So in the last class, we started looking at heat exchangers. Let me share the file. Is it visible? Slides are visible to everyone?
Yes, sir.
Okay, thank you. Okay. So in the last class, we said that, studying the heat exchanger and its design is extremely important, because if you look at the process application, several heat exchangers are regularly used in the process application. Some of the commonly used heat exchangers are shown here: a double pipe heat exchanger, plate type heat exchanger, spiral heat exchanger, air cooler heat exchanger, shell and tube heat exchanger, etc. Then we started looking at a very simple design of double pipe heat exchanger, where we said that double pipe heat exchanger has two concentric pipes. From the inner pipe, one fluid flows, whereas in the annular region, another fluid flows, and both these fluids interchange the heat with each other. Okay, so both the fluids are separated by a metal wall in between. Again, the generalized version of this double pipe heat exchanger is a shell and tube heat exchanger, where there is a bigger size pipe is there, and inside that bigger size pipe there are several small size tubes are there. Such arrangement is called as shell and tube heat exchanger. So outer bigger size pipe is called as a shell, whereas all the inside pipes are called as tubes. Okay, so this is a typical schematic of the shell and tube heat exchanger. Here you can see that this is 1-2 pass shell and tube heat exchanger, where the shell side fluid is passing through the heat exchanger only once. That's why it is called as one shell side pass. Whereas in the tube side pass, here you can see that the fluid is flowing through these tubes and then again changing the direction and coming from this another two tubes. So there are two tube side passes are there. So this particular arrangement is called as 1-2 shell and tube heat exchanger. So first one represents shell side pass, the next digit 2 represents tube side pass. So typically the shell and tube heat exchangers are 1-2 shell and tube heat exchanger, 2-4 shell and tube heat exchanger, or 2-6 shell and tube heat exchanger, etc. Okay. Then we started looking at different parts of the shell and tube heat exchanger. This is what we have seen. So shell and tube heat exchanger has several parts. We have discussed these parts also. So we can have this stationary bonnet head here on the left hand side. We can have the channel cover on the right hand side here. These tubes are there. These tubes are fitted in this circular disc, which is called as a tube sheet. This tube sheet is fixed to the stationary bonnet head using this flange. This shell also has this expansion joint, because the material of construction of shell and tube could be different, and because of that the expansion of tubes and shell could be with a different rate, and in order to manage that, the expansion joint is there. In order to have the turbulence of the fluid for a shell side fluid flow, the baffles are added, and this baffles spacing is arranged using the baffle spacer and tie rod. This entire shell and tube heat exchanger is fixed using the heat exchanger support. There are nozzles for input of the shell fluid as well as tube side fluid. So these are the different, parts which are commonly present in the shell and tube heat exchanger. Typically, shell and tube heat exchanger, there are different types of shell and tube heat exchanger depending on what type of head is used here, what type of head is used here, and what type of body is used in between. Based on that, there are different types of shell and tube heat exchanger, and the classification of the shell and tube heat exchanger is given by this TIMA institution, which is nothing but Tubular Exchanger Manufacturers Association. So based on what is the front end, what is the shell type, and what is the rear end, depending on that, different types are there. Okay, so which could be one pass shell, two pass shell, split flow, double pipe, double split flow, divided flow, kettle type boiler, etc., cross flow. These are the different shell types. In a front end, we can have a stationary front end. If you look at, it can be channel and removable cover, bonnet type of cover, etc. In a rear end, we can have again a different types. So based on these different types of the shell and tube heat exchangers are there. We will not go in the detail of this. This information is given in order to make you aware that if you work in the industry, depending on your requirement, if you wanted to design a shell and tube heat exchanger, where you have to look different design is this Tubular Exchanger Manufacturing Association. This particular, institution, if you look at the documents by this particular institute, you will get different designs, and you have to select some of these designs based on whatever is suitable to your case. Okay, all right. Apart from shell and tube heat exchanger, the commonly used compact design heat exchanger is a plate and frame type of heat exchanger. Another interesting, information about the plate and frame heat exchanger is very high heat transfer coefficient can be obtained in plate and frame heat exchanger. The only drawback of this particular heat exchanger is there is a large pressure drop is present, and also cleaning of plate and frame heat exchanger is slightly difficult. Okay, so how this particular heat exchanger work? Here you can see that there are different plates are there, and in between these different plates, in the cavity between these two plates, you can see in this cavity the hot fluid is present, whereas the adjacent cavity here there is a cold fluid is present, and this cold fluid and the hot fluid exchanges heats across this particular plate, and this plate could be again corrugated or different fins are there, isn't it? So here I have shown two types of corrugated plate. One is the chevron type of plate, and another one is the washboard type of plate. Okay, so these corrugations basically increases the heat transfer coefficient and rate of heat transfer. Okay, but as you can see that this is a very compact design. Here the fluid has to come from this nozzle, fill this entire cavity, and then it goes out from this another nozzle, and so in alternate plates you can see that the flow changes the direction. So here it goes like this, then comes down, then goes straight, again it comes up. So you can see that the fluid, both the cold and the hot fluid, flows through a tortuous path, and because of that there is a high pressure drop takes place. Okay, is it clear to everyone? Hello?
Yes,
Hello?
sir, clear.
Okay, so so you can see the whatever the discussion we had, that discussion itself is written here. So this is one of the most compact design in which multiple vertical plates are clamped in a press or frame such that between successive cavities hot and cold fluid flows. The streams between alternate plates are directed by gaskets, which are also used for preventing the external leakage. Again, these plates are made up of stainless steel or higher quality material. Also, these could be corrugated as shown here. Okay, so because of this corrugation, the fluid flows in a tortuous path, and which increases the rate of heat transfer significantly. Okay, the another type of heat exchanger is a air cool or a fin fan heat exchanger. So here you can see that the fluid which we wanted to cool flows through this tube isn't it? And comes out from this another tube here. Fluid inlet is this, fluid outlet is this, and this tube along this path is blown by air by using a fan, or sucked. Air is sucked or blown over this tube using a fan. Okay, so what happens is the air which is blown across these tubes takes the heat from these fluid flowing through these tubes. Okay, again, in order to increase the rate of heat transfer, you can see that the fins are used around these tubes. Is it clear to everyone? Hello, is it clear? So this type of heat exchangers are regularly used in the industry when you wanted to cool down some liquid or some the waste gases coming out using the air. Okay, all right. Hello, is it clear to everyone?
Yes, sir. Clear.
Okay. Spiral type of heat exchanger is shown here. Here you can see that the spiral type of heat exchanger is shown here. So you can see that hot fluid enters from the center and comes out from the periphery, whereas the cold fluid enters from the periphery and comes out from the center. And in between these cavities, cold and the hot fluid is flowing. So you can see that the hot fluid is shown by a red or a orange color here, whereas the cold fluid is shown by this blue color. Okay, so a typical design is like this. You can see that the hot fluid is entering here, and then it follows a spiral path like this and comes out directly from here, whereas the cold fluid comes here at the periphery and follows the spiral path and finally comes out from the center. Okay, so this design is regularly used in the process industry. So how this type of heat exchanger is basically constructed? They use a long plates, and these plates are wrapped in a spiral manner. Okay, so that's how the spiral heat exchanger is constructed. So you can see that the figure of the spiral heat exchanger is also shown. This is something like a spiral heat exchanger. Here you can see that from the center the hot fluid is entering, coming out from the periphery. Similarly, the cold fluid comes in from the periphery and comes out from the center, somewhere like this. Okay. This type of heat exchanger is regularly used whenever one of the fluid is fouling. Okay, so in many difficult applications where fouling and plugging is, what is fouling? Fouling is nothing but whenever the fluid is flowing through a heat exchanger, it starts depositing the solid material over the metal surface. That is called as a fouling. Okay, fouling or plugging. So if the dirt or some solid material is settling on the metal plate, it reduces the heat transfer area. So fouling is a very important thing to look at in a process industry. So you can see that all these heat exchangers are regularly cleaned in order to remove the dirt or a foul which is deposited on the metal surface of the heat exchanger. Is it clear to everyone?
Sir, but the dirt can also result in heat exchange, isn't it?
The dirt can also result in
heat exchange.
So see, okay, in comparison with the metal, the dirt which is settling on the plate will have a lower heat transfer coefficient, isn't it? Metal will have a very high heat transfer coefficient. So it acts as a resistance. It acts as a resistance, so it reduces the rate of heat transfer. So typically all the heat exchangers has to be cleaned over the period. Typically, if you look at the shell and tube heat exchanger, in a shell and tube heat exchanger also we clean the tubes, we clean the shell regularly. Okay, but cleaning the tubes and the shells in the shell and tube heat exchanger is slightly difficult compared to if you look at the spiral heat exchanger. In a spiral heat exchanger, the cleaning is easier. Okay, that's what is written here. Again, the spiral heat exchanger is costlier, but once you have constructed the things, then the lower life cycle cost is there because the lower fouling rates and easier maintenance is there. So that's why the initial cost is higher, but then maintenance cost and the other cost is lower for the spiral heat exchanger. Okay. So now let's look at what are the different complications comes when we look at the heat exchanger. A typical example is a shell and tube heat exchanger, which is regularly used in the process application. So this is 1-2 pass shell and tube heat exchanger. Here you can see that the hot fluid is entering through the shell like this, follow this tortuous path and comes out here. So there is one pass of the hot fluid coming from here and going out from here, whereas the cold fluid is coming in through this another nozzle here, and the cold fluid is flowing through these tubes. Again the fluid is changing the path in the second pass and then coming out through this another nozzle. So here you can see that the cold fluid is having two passes because it is flowing through tubes, whereas the hot fluid is having only one pass because it is passing through the shell. Can you see the point? Hello? At least the system is clear to everyone what I'm saying. Hello?
So can you repeat the system?
Okay. So here you can see that in a shell and tube heat exchanger, what we are looking at is there is a heat exchange between the hot and the cold fluid. Now in this case, the hot fluid is flowing through the shell. So here you can see that the hot fluid is entering through this shell nozzle here, entering through this TH1 is the input temperature of the hot fluid. And this hot fluid is following this tortuous path and finally coming out from this outside nozzle here, isn't it? So this shell side fluid is flowing only in one direction like this, isn't it? In this direction, correct? So only one shell side pass is there. Whereas the cold fluid is entering here, passing through this tube, changes the direction and coming back through these tubes and finally coming out from the tube like this, isn't it? Coming out from this nozzle like this. So here you can see that the cold fluid is having two passes. One pass is this and the second pass is in the reverse direction. Can you see the point now? Is it clear?
Yes, sir. Now it is clear.
Now let us plot its temperature. Let's plot its temperature. So as I said, the hot fluid is having only one pass from left to right. If I plot how this hot fluid temperature is decreasing between this input and this output. So TH1 we are starting and at the end 2 the temperature is decreasing. This is okay. This hot fluid which is shown by a red line and the arrow is also shown which shows the flow direction. Is it clear? Is it clear? This graph is clear. So yes, I have plotted the temperature versus distance here. So temperature versus distance of the hot fluid I have shown by a red line here. Now in a similar manner, I have plotted the cold fluid also. So how the temperature of the cold fluid varies along the length of the tube. So we are starting from this end 1, isn't it? So initially the temperature increases because this cold fluid you can see that is also flowing along the direction of the hot fluid. So this direction, you can see this direction of the cold fluid here in the first pass is same as the direction of the hot fluid. Once I reach to this end, then this cold fluid changes the direction and comes back like this, isn't it? And finally reaches to the TC2. Is it clear? The second graph, this which is shown by a blue color, is clear to everyone?
Yes, sir.
Now another interesting thing to look at it. So far we were looking at only co-current or a counter current contacting, isn't it? Whether both the fluids are flowing along the same direction or in the opposite direction. Only this part we were looking at. When both the fluids were moving along the opposite direction, then we call that design as a counter current flow. When both the fluids were flowing along the same direction, we call that design as a co-current flow. But in this case, you can see that the fluids are flowing both in counter current and co-current, isn't it? Do you agree with me?
Yes, sir.
Along with that, if you look at carefully, if you look at the flow of this hot fluid, See, cold fluid is flowing in a same direction. It's not following a tortuous path in the tube at all. It is flowing directly in this direction. But if you look at the shell side fluid, it is moving up, coming down, moving up, coming down. It follows a tortuous path because of the presence of these baffles. So these baffles are what? These are nothing but 75% cut, 25% cut cylindrical, circular disc are there, which basically channels the direction of the flow. Okay. So you can see that the flow of the shell side fluid is a tortuous. It is not exactly a parallel. It could, you can call it as a cross flow in a way. Do you agree with me? Do you agree with me or not?
Yes, sir.
So if I let me just arrange it. Okay. So if I look at the direction, even though I am saying these are flowing, the hot fluid is flowing in this direction and the cold fluid is flowing in both in this or as well as this direction, but actually the hot fluid is not flowing following this straight line like this. Cold fluid are following this straight line, but hot fluid is not following the straight line, isn't it? It could be it is following a tortuous path like this, isn't it? So that means at some location, if I show by a different color, so in a way this is the cold fluid is flowing, but the hot fluid is moving, the hot fluid is moving in this direction, then coming back like this, then moving this direction, then coming back like this, isn't it? Do you agree with me?
Yes, sir.
So it is in a way is a cross flow. It's a mix of cross flow. It's a mix of co-current flow. It's a mix of counter current flow. You will not be able to say that it is exactly a counter current flow or a co-current flow. Do you agree with me?
Yes, sir.
And that is the reason why we use another factor in this equation, which is called as correction factor. Typically the equation is what? The heat transfer is given as UA delta T LMTD in this case, isn't it? Because the delta T, the temperature change between hot and cold fluid is changing along this length, and therefore log mean temperature is used. But in addition to this log mean temperature correction factor is used here. Because our flow is not counter current, our flow is not co-current, it is a cross flow, it is a mix of cross flow, co-current flow and counter current flow. Everything is there. Do you agree with me?
Yes, sir.
Can you see the rationale behind why this LMTD correction factor is used here? Make sense to everyone?
Yes.
My
sir.
slides are visible?
Yes, sir.
Okay, so that is what is written here. In a multi-pass heat exchangers, which we have both co-current and counter current temperature profiles, and therefore a correction factor FT is needed. Now, how to calculate this FT? How to calculate this FT? So typically, in order to calculate in a multi-pass heat exchanger, when I am saying a multi-pass heat exchanger, what I mean by multi-pass? So this 1-2 pass heat exchanger is a multi-pass because here one shell side pass is there and 2 tube side pass is there. Similarly, I can have 2-4 heat exchanger, shell and tube heat exchanger. So 2 shell side pass and 4 tube side passes can be there, isn't it? So all such heat exchangers are called as a multi-pass heat exchangers. Okay? Does it make sense to everyone? Hello?
Yes, sir.
Okay. So how these things are then, accounted? So typically, whenever we have a multi-pass shell and tube heat exchanger, in order to design the shell and tube heat exchanger, first we calculate the TC. Now there are two quantities, tau C and R. What is tau C? Tau C is in a way is a efficiency. In some of the books, this tau C is represented by eta. Efficiency is typically shown by a eta. So what this tau C is? you can see that the numerator here is Tc2 minus Tc1. Tc2 minus Tc1 is what? The sensible heat or the temperature increase gained by cold fluid. Tc2 minus Tc1 is the temperature increase gained by the cold fluid, isn't it? Tc1 is the initial temperature of the cold fluid. Tc2 is the outlet temperature of the cold fluid, isn't it? And the difference between that will be what? The temperature increase of the cold fluid. Do you all agree with me? Yes or no?
Yes, sir.
And this quantity is divided by the maximum temperature gradient or temperature difference present in the heat exchanger. Now, what could be the maximum temperature difference present in the heat exchanger? If I go back here, what could be the temperature, maximum temperature difference I can have in this heat exchanger? That could be TH1 minus TC1. Yes or no? That will be the largest temperature difference, isn't it?
Yes, sir.
So here you can see this tau C is nothing but the temperature increase of the cold fluid divided by maximum temperature difference present in the heat exchanger. So that is the theoretical limit. That is the theoretical limit. We are dividing that theoretical temperature difference, maximum temperature difference which is present. So this particular quantity is similar to the efficiency. We don't call it as efficiency, but this is similar to the efficiency. There is another quantity R. This another quantity is how much is the drop in the hot fluid temperature. So hot fluid entering in the heat exchanger with the temperature of TH1 and eventually it releases the heat to the cold fluid and its temperature decreases to TH2. So TH1 minus TH2 is nothing but the drop in the temperature of the hot fluid divided by increase in the temperature of the cold fluid, and this particular quantity is defined as R. How? Now these two quantities tau C and R are used to calculate the F factor. So there are several graphs are given in the book. So typically the graphs are given which are shown, a typical graph is shown here. So in this particular graph, Ft versus tau C is plotted, and in this particular plot there are different curves which are shown by red are there for a typical value of R. So how we calculate the Ft? First we calculate this tau C, then we calculate the R value. So once we know the value of R, we select a particular graph corresponding to that R. Let's say this R value comes out to be 0.5. So I will select this graph of R equals to 0.5. And then I look at the value of tau C. So let's say this tau C value is somewhere here 0.2. So in that case, my Ft value I can calculate like this. So let's say here I will have 0.2, isn't it? So if I extrapolate this line on this R curve here, so somewhere here I will get the value of Ft factor for this case. Is it clear? This is how we calculate the Ft factor using different graphs. So in the book you can see that 2.4 or 2.6 or 1.2 heat exchanger, all these graphs are given in the book. All these graphs are given in the book. One can use those graphs and calculate the Ft value, and that Ft value has to be multiplied here in the LMTD to calculate the Q. Again, for a simple case of 1-2 pass heat exchanger, a analytical expression for Ft is also I have given here. Is my slides visible to everyone?
Sir, they right now unshared.
Just share. Is it visible?
Yes, sir.
Okay, thank you. So first we calculate the value of R, then we calculate the value of tau C, and then we look at these graphs of Ft versus tau C which are there in the book, isn't it? So these graphs are given for different designs like 1-2 pass, 2-4 pass, 2, 6 pass, etc. And corresponding to a particular graph, we select the line for R and then we select the value of tau c. Draw a parallel line here which is parallel to this y-axis and select the value of ft corresponding to that value. And that ft value we use in the LMTD correction factor in order to calculate the Q. Okay, but for a simple design of 1-2 pass, a analytical expression of ft is also given here in the slide. For 1-2 pass, if you don't want it to use this graph, you can put the value of R and tau c in this equation and you can calculate the ft value directly without looking at the graph itself. Another interesting thing to note down, no matter what type of multi-pass heat exchanger you are using, but if one of your fluid is condensing, this word is very important. If one of your fluid is condensing either in a shell or in a tube, in that case, the F factor is equals to just 1. Okay, so can you see the point? Why we have looked at the correction factor? Is it clear to everyone? Hello?
Yes, sir.
And another important part is how to calculate that F factor. So in this slide, we are looking at how to calculate that F factor. Okay. So a typical way of doing it using these graphs, but also for a 1-2 pass heat exchanger, you can calculate the FT factor using this analytical expression. Okay. Another interesting thing which I have talked about is if one of the fluid is condensing. Remember in the heat exchanger, both the fluids are these are releasing the heat. One fluid is releasing the energy, whereas the another fluid is gaining the energy. But very often we can use the condensing steam. That means we are using a saturated steam. So that fluid is not changing the temperature along the length of the path, length of the heat exchanger, isn't it? Do you agree with me or not? Let's say if I say that this hot fluid is a steam. This steam is condensing steam. So what type of temperature profile I will get if I am using the condensing steam or a saturated steam here? Then I will, instead of having this, I will get just a parallel line. Do you agree with me?
Yes, sir.
So in such cases, this FT factor is just 1. Is it clear to everyone?
Yes, sir.
Okay. Another interesting, is my slides visible or I lost?
Not visible.
Hello? Hello? Is my slides visible or
No, sir, not visible.
not visible? Acha. Just a minute. Is it visible now?
Yes, sir.
Okay. So another interesting, comparison between single pass and multi pass is given. Remember, that is what one of the question one of the student asked me in the last class. What happens if we increase the multi passes? So let's say if you are having a single pass tube side pass and if you are having the 4 tube side pass, what are the different quantities and how these are going to change? So if we are having a 4 tube side pass heat exchanger, and if I compare that with the single tube side pass heat exchanger, in that case you can see that the tube velocity in the 4 pass heat exchanger will be 4 times the single pass. Tube side heat transfer coefficient is 4 raised to the power 0.8, so that is almost 3 times higher. Delta P, that is nothing but the pressure drop across the heat exchanger, is almost 4 raised to the power 1.8. So that comes around 12 times, almost 12 times higher than the single pass. Frictional losses are higher by almost 2.8 times. That is 48 times higher than the single pass. Also, the length of the So length here, length, if you look at the length will be with respect to single pass, the length will be 1/4 times. Okay, this some mistake is there. So length will be 1/4 times than the single pass. Is it clear? Is it clear to everyone?
Sir, how will length decrease?
So see what you are doing. Maybe I'll just go back. What we are doing, instead of having a very long pipe, you are basically making a tortuous path like this. Is it okay? So this total length here of the heat exchanger will be 1/4 times the length, total length. Otherwise you require. Is it clear?
Yes, sir.
So see, maybe I'll just draw it. So see, if I can have a very long, I can have a very long heat exchanger like this, isn't it? Where only one shell pass is there and one tube pass is there. So one tube pass means we will have only one this annular region around it, isn't it? Or I can have a tortuous path like this, isn't it? For a tube side. So this one pass, this is two pass, this is three pass, this is four pass, this is five pass, and this six pass. So now this total length will be what? 1/4 times this length. Do you agree or not?
Yes, sir. Got it.
Okay. So this is this example which I have given is a commonly asked example in the is my slides visible or lost? Hello? Huh?
Visible.
Visible. Okay. All right. So this is the commonly asked example in the interviews. Okay. Very often if you give a interviews to some PSUs, this is what in general they ask. Okay. If you increase your pass by 2 times instead of single pass, if you are having a 2 pass, what will be the tube velocity? Tube velocity will be twice. Tube heat exchanger coefficient will be what? In a 2 pass, 2 raised to the power 0.8. Delta P by length will be what? 2 raised to the power 1/8. Here this 4 is coming because what? Because of what? This 4 is coming because 4 pass are used. But let's say if you are having a 2 pass instead of this 4, it will be 2, isn't it? Is it clear to everyone? Is it clear to everyone?
Yes, sir.
So this last point I will check. I think this is with respect to the length of the heat exchanger is also same in this case. Okay. So length of the heat exchanger, the overall length is same, but the flow length will be 4 times the single pass, isn't it? Correct? This I will check. Okay. So if the length of the heat exchanger is same, how many times this is repeated? 4 times. So that will be 4 times the single pass length, isn't it? Correct? Right? Is it clear or not clear?
Yes, sir. Clear.
Okay. All right. Okay. So let's look at now how to design the heat exchangers. Maybe before that, let's look at one simple, concept of fouling. As I said that typically in a heat exchanger over the operation, this dirt and the foul get deposited, and because of that, the heat transfer coefficient decreases drastically. So whatever the heat transfer you have obtained for a clean heat exchanger may not be the rate of heat transfer you will get in an actual operation, isn't it? So how to account the fouling factor is shown in this slide. So let's look at the cylindrical type of heat exchanger here. So this is the tube. You can assume that this is as a tube. So H0 is the outside heat transfer coefficient, HI is the inside heat transfer coefficient. This tube is made up of a solid material, so thermal conductivity is K. Thickness of this tube is R0 minus R. Outer radius of this tube is R0 and inner radius is Ri. So in a clean type of tube, let's say this tube is clean, there is no dirt, there is no fouling on the surface. In that case, the overall heat transfer coefficient using the outside surface area can be obtained using this equation, isn't it? This equation we have seen earlier. Do you agree with me? 1 by U0 is given as 1 by H0 plus R0 by K ln R0 by Ri plus R0 by Ri 1 by Hi. So this first expression is defined when we are looking at the overall heat transfer coefficient with respect to the outside surface area. In a similar manner, if you are defining the overall heat transfer coefficient with respect to the inside surface area, then this equation changes to this another equation, which is 1 by Ui is given as 1 by Hi plus Ri by K ln R0 by Ri plus Ri by R0 1 by H0. So both these equations 4 and 5 are valid, and one has to use U0 or Ui depending on which surface area you are accounting in a Newton's law of cooling. Yes or no? Do you agree with me?
Yes, sir.
Now, these two equations are valid only if your heat exchanger is clean. But in a regular operation, your heat exchanger is not at all clean. Very often, lot of material get deposited during the process operation, isn't it? And because of that, there is a fouling and dirt deposition is taking place on the surface of the heat exchanger, inside as well as outside. And this dirt deposited inside and outside of this metal wall is called as what? Fouling. This is called as a fouling. And the heat transfer resistance offered by this is called as a fouling resistance, RF. Okay. So typically this scaling and fouling is occurring because of impurities in the fluid, chemical reaction and rusting of the metal surface, etc. Okay. How these fouling factors are accounted in calculating the overall heat transfer coefficient. So instead of using 1 by U0 for a clean surface, we use the 1 by U foul, because that is what actually you will see in a operation, isn't it? You have designed the heat exchanger. One day it will be clean, but that heat exchanger you will continue for 2 months, 3 months before you clean it, isn't it? So during your regular operation, your heat exchanger is often fouled, isn't it? So if you are calculating your heat transfer rate of heat transfer using the clean value of this U0 or Ui, that will not be valid, isn't it? Do you agree with me? Do you all agree with me?
Yes, sir.
So we have to include this additional resistance, which is called as a fouling resistance. And this fouling resistance is just added in 1 by U0 expression like this. So 1 by U foul is given as Ra plus 1 by U clean. Now depending on whether we are using the expression for U0 or Ui, that is added here. You can see if you are using for U0, it is given as 1 by U0 is equals to 1 by H0 plus RFO. RFO is nothing but the fouling factor with respect to the outside surface here. So fouling taking place here outside surface plus this R0 by K ln R0 by Ri, this remain as it is. This last R0 by Ri 1 by Hi, this also remains as it is. But additionally, the fouling which takes place inside surface here, that can also be accounted through this R0 by Ri RFI, where RFI is nothing but the fouling resistance taking place inside this tube. So here R0 by Ri we have dividing because this U0 is defined in terms of the outer surface area, and therefore this R0 by Ri we have to multiply here. Isn't it the same way we have multiplied this R0 by Ri in this 1 by Hi, because this Hi is the heat transfer coefficient for inside. Can you see the point? Hello?
So
Is it clear?
when the fouling is there, the inner surface would not be exposed to the fluid, so there shouldn't be any point of using 1 upon Hi in that case.
No. So fouling, what you are saying, this, see, if you are saying that this entire surface will be uniformly added with the dirt, that's what you are saying?
Yes, sir. Yes, sir.
It's not like that. It's not like that. It's not that the entire surface will be fouled. It will be fouled in patches here and there.
Okay.
Okay, so both
Yes.
these HI and RFI both will be present. But your point is very well taken. Okay, is it clear? Does it make sense to everyone?
Yes, sir.
Okay. So similarly, we can define the expression, similar expression for with respect to UI. So UI will be given by 1 by UI is given as 1 by HI, RFI. So similar to this, but here RFI will be added, and in addition to that, RI by R0 into RFO will be added here additional. So this factor and these two factors has to be added here in equation number 5. Is it clear to everyone? So this additional factor and this additional factor has to be added in this equation number 5 to get equation number 8. Is it clear to everyone? Make sense?
Yes, sir.
Okay, let's look at one problem. Okay, so determine the overall heat transfer coefficient U0 based on the outer surface of a 2.54 centimeter outer diameter, 2.286 centimeter inner diameter heat exchanger tube with thermal conductivity of 102 watt per meter Kelvin. If the heat transfer coefficient at the inside and outside of the tube are given as HI is given as 5500 watt per meter square Kelvin and H0 is given as 3800 watt per meter square Kelvin respectively, and the fouling factors are given as 0.0002 meter square Kelvin per watt. Okay, so now let's calculate the overall heat transfer coefficient in terms of the outer surface area. So this is the same equation which we have seen. 1 by U0 is given as 1 by H0 plus RFO plus R0 by K ln R0 by Ri plus R0 by Ri RFI plus R0 by Ri 1 by HI. So if you put all the values here, so here RFO and RFI both are given as 0.002. So if you put all these values, my overall heat transfer coefficient comes out to be 1110 watt per meter square Kelvin. Clear? Is it clear? If I calculate this without the fouling factor, let's see what I get. If I calculate this without the fouling factor, then what value I am getting, let me just calculate that. 3800 inverse plus 0.0127 bhagila 102 multiplied by ln 2.54 divided by 2.867 plus 2.54 divided by 2.867 into 5500 inverse. So this becomes okay. So if you do not use these fouling factors, then your value comes out to be 2444. Okay. So clearly you can see that with the fouling of the heat exchanger taking place, your heat transfer decreases significantly, almost half. Can you see the point? Hello?
Yes, sir.
So if you calculate the maybe I just write here for clean heat exchangers, the overall heat transfer coefficient U0 is 2444 at meter square Kelvin. This is what you are expected to get. So you can see that almost there is a 50% decrease in the rate of heat transfer. There is a 50% decrease in the rate of heat transfer. So fouling is a very important factor to look at. If you join a industry, then this factor is going to be really significant. Don't ignore it. Okay. Is it clear to everyone? Is it clear to everyone?
So
Okay. Is my slides visible?
Yes, sir.
Okay. Let me just make it full screen. Okay. So now let's look at how the heat exchangers are designed. So let's look at how the shell and tube heat exchangers are designed. So this particular design method is called as a Kern method, or in a simple language, it is referred as a LMTD method. Okay, this method is called as a LMTD method. Now, designing the heat exchanger is not an easy job. It's not an easy job. Why I'm saying it's not an easy job? Because typically you have a limited space available in the industry, isn't it? So if you have no restriction on the space, in that case, instead of using a shell and tube heat exchanger, probably you will use a double pipe heat exchanger, isn't it? Because the pressure drop will be minimal in the double pipe heat exchanger. But you make the tubes to coiled, and then because of that you increase the number of passes so that you get a compact design. Instead of having a long heat exchanger, you get a compact heat exchanger, but that lead to a higher pressure drop. So there is a trial and error present in this entire design procedure, because if you make more number of passes, what happens is the pressure at both shell and tube side increases. If you are increasing the number of passes, definitely it is increasing the heat transfer coefficient. But some limit is there on how much pressure you should have in a tube side, how much pressure you should have in a shell side. Okay, so depending on that, you have to select a design which gives you a very sufficiently high value of heat transfer coefficient, and at the same time your pressure drop is not increasing significantly. That design you have to select. So there is a trial and error associated with this entire design problem. Okay, let me give you a glimpse of that. We will not solve any problem, but I will try to give you a glimpse why I am saying that it is not a straightforward exercise. Okay, in fact, one of the tutorial, when we will do a tutorial, there you will see that why I am saying that there is a trial and error. One such tutorial is there where we are doing it for several iterations to get the correct design. Okay, so how we can calculate the heat transfer coefficient? So heat transfer coefficient we have to calculate both in a shell side as well as tube side. Once we get the heat transfer coefficient in a shell side and tube side, and remember that the shell side heat transfer coefficient and the tube side heat transfer coefficient depends on how many passes you are using. Whether it is 1-2 pass, whether it is 2-4 pass, whether it is 2-6 pass heat exchanger, depending on that you will get a different heat transfer coefficient. Okay, so heat transfer coefficient in a shell side can be obtained using this equation. H naught dH divided by K naught is given as 0.36, dH GS divided by mu raised to the power 0.55, Cp mu by K naught raised to the power 0.33, and mu by mu naught mu W raised to the power 0.14. So here this first bracket basically corresponds to the Reynolds number. The second bracket corresponds to the Prandtl number, and this is nothing but the viscosity correction factor which we have seen in a Cedar and Tate correlation earlier. Okay, but this is not the Dittus-Boelter equation. This is slightly different than that. And why? Because we are not having a pi flow here. What type of situation we are having? The situation which we are looking at here is not exactly a pi flow, but slightly different than that. Here you can see that we are having a bigger size pipe which is called as a shell, and inside that there are different tubes are there. Correct? Do you agree with me? So because of that, it's not completely a pi flow. It's not completely a pi flow. There are different obstructions are there, and sometimes there are baffles are also there. Therefore, this equation, Nusselt number equation, is slightly different compared to the Dittus-Boelter equation. Again, here this DH is nothing but what? This DH is nothing but the hydraulic diameter. It's nothing but the hydraulic diameter, because we are not talking about this entire diameter, because the flow area is getting restricted here because of these tubes present here. And this hydraulic diameter also depends on how these tubes are arranged, whether these tubes are arranged in a proper circular type of design. If these are arranged in a proper circular type of design, then it is called as a then it is called as a proper rectangular type of design, then it is called as a rectangular pitch. This is called as a rectangular pitch. Rectangular pitch. And the distance is this given by P here. When these are arranged in a triangular shape like this, then this is called as a, this type are called as a triangular pitch. Triangular pitch. One should note down here is typically the triangular pitch gives a higher rate of heat transfer compared to this square pitch, rectangular or a square pitch. Okay, in a square pitch, the rate of heat transfer is lower, but it is easy to clean. This is easy to clean. Easy to clean compared to this, compared to the triangular pitch. Okay. So depending on whether we are using a square pitch or a triangular pitch, this hydraulic radius expression will be different. So for a square pitch, we get a hydraulic radius like this, where for triangular pitch, we get a hydraulic radius slightly different. Again, you can note down that here the hydraulic radius is calculated in a different way compared to when we are calculating the hydraulic radius for a pressure problem. Remember, in a pressure problem, the weighted perimeter is a different thing, isn't it? In a heat transfer problem, this hydraulic radius, hydraulic diameter is calculated in a slightly different way. Okay. So once we get this hydraulic diameter here, we can put that hydraulic diameter in this equation. And then we can calculate the shell side heat exchange heat transfer coefficient. Similarly, we can calculate the tube side heat transfer coefficient. How we can calculate the tube side heat transfer coefficient? Anyone? Can you say? What will be the tube side heat transfer coefficient? For tube side, I have given only a shell side. This is only a shell side. Okay. What will be the tube side? For tube side, we have to use Dittus-Boelter equation that we have seen earlier. So what is Dittus-Boelter equation? Nusselt number is given as 0.023, Reynolds number 0.8, Prandtl number raised to the power 0.3 or 0.4, depending on whether you are looking at heating or cooling, isn't it? So this equation you have to use, and based on that you can calculate the heat transfer coefficient for the tube side. Using this, you can calculate the heat transfer coefficient for the shell side. Once you get the shell side and tube side heat transfer coefficient, you can use this in a equation to calculate the overall heat transfer coefficient, and that overall heat transfer coefficient you will be multiplied to a LMTD correction factor, LMTD, and area of the heat exchanger, and you will calculate the rate of heat transfer, Q. So Q will be given by, let me write down somewhere. Okay, let me write down here. Q will be given as UAFT factor into delta T LMTD. So this U will be calculated using this H0 and HI, where H0 is what? Shell side, and HI is what? Tube side. So once you get H0 and HI, you can calculate Q. Okay. Now, why there is a trial and error? There is a trial and error because so far you have calculated only the heat transfer. Now let's look at the flow problem also. So flow problem is we have to calculate what will be the pressure drop in a tube side. So tube side pressure drop can be obtained using this equation. FGT square ln divided by 2G rho T di phi T, where phi T is this viscosity correction factor, GT is nothing but the mass velocity of the fluid, L is the tube length, F is the fanning friction factor. This fanning friction factor you can get from this Moody's plot, which is nothing but F versus Reynolds number plot. So once you get this fanning friction factor for a given Reynolds number, you can put it in this equation. You can calculate delta PT. Again, remember, in a multiple pass heat exchanger, the tubes are moving like this, isn't it? Correct. Depending on how many passes you are having, and depending on that, because the direction change of the velocity is taking place, and because of that there is a pressure drop, and this pressure drop is referred as a return loss, and this return loss is calculated by using this equation delta PR. which is given as 4n v square by 2g into rho t. Here n is the number of tubes used, and the summation of delta PR and delta PT is the total pressure drop. This is the total pressure drop taking place in the tube. Similarly, we can calculate the total pressure drop taking place in a shell. That is again calculated using this equation. This equation and this earlier equation is same. The only difference here is the subscripts are replaced by S. So now everything we are looking at a shell side. So mass flow rate at a shell side is given by GS. Fs is the shell side frictional loss, friction factor. Phi S is nothing but the shell side viscosity correction factor. Rho S is the density of the shell side fluid. DH, capital DH is the hydraulic radius. Now this hydraulic radius here is calculated slightly differently. This hydraulic radius calculated here accounts the total surface area weighted. But here this hydraulic radius we have calculated. This is slightly different. Okay, this only looks at heat transfer. Remember, for a heat transfer, hydraulic radius calculated is slightly different way compared to if you are calculating it for a pressure drop. So once we calculate this hydraulic radius here, we can put it here, hydraulic diameter here, we can put it in this equation, calculate delta PS. And now this delta PT and delta PS we have to check. We have to check whether this delta PT and delta PS, these values are operable range or not. If these are not in the operable range, then we have to go back again to our design and change from 1-2 pass to 2-4 pass or 2-4 pass to 1-2 pass, change the length of the heat exchanger, change the temperature present in the heat exchanger, and finally come up with the design which not only satisfies this delta PT requirement, but also satisfies the requirement of this U. That's why there is a trial and error. Can you see the point? Hello?
Yes, sir.
So this is a very practical application, guys. If you join a industry, this is what you are going to do. If you are designing, even if you are not going a proper process application, you might join some EPC companies. EPC companies like Foster Wheeler or Jacob, etc. Isn't it? They also pays huge salary to the students. There you will be designing this entire thing on a computer. But all these small details you are going to use there. Okay, is it clear to everyone?
Yes, sir.
Does it make sense?
Yes, sir.
So the point I wanted to make here is this particular methodology is called as a Kern method, or this is also called as a LMTD method. Okay, let me just erase whatever I have written here. There are interesting problems solved in the book. Okay, on this, I'm not going to do any problem on this. Some 1 or 2 problems solved on a similar line. Very practical examples solved in a book. The reason behind that is because BK Datta was an industry man. He worked as a chairman for Bengal Pollution Control Board, and currently he is a visiting faculty at IIT Kharagpur. So a lot of examples given with respect to these has a interesting practical aspect associated with it. Okay, so please look at the solved example. Is it clear to everyone? Is my slides visible?
Yes, sir.
Okay, all right. Okay, let's digress from this Kern method. These are really interesting things. I don't know whether you are finding it interesting or not. So I ask a simple question to all of you. What is the drawback of this method? Can you tell me what is the drawback? I have partially given you the answer. In the discussion itself, I have partially given you the answer. What is the drawback of this Kern method or LMTD method? Anyone?
Trial and error probably.
Okay, that is one drawback. Okay, any other? Come on, guys, you are all are JEE pass out students. Apply your brain.
Fouling.
Fouling is going to take place in all the heat exchangers. I am talking about what is the drawback of designing method. Remember, this methodology is called as a Kern method. There is another method. There is another method which is called as effectiveness NTU method that we will look at. But before we go there, let us appreciate what is the drawback of this. Why we need another method. Why can't we go this? There is no technical problem in this entire method. There is no technical problem. Fouling, that is anyway a practical phenomena that we have to account, isn't it? Trial and error that we have to account. But there is a major drawback in this method. Major drawback in this method. Major drawback in the sense that that drawback you can get rid of, but then you will have to do lot of trial and error things to get rid of that drawback. But there is one significant drawback is there. Can anybody think? Okay. So the major drawback in this methodology is you require all terminal temperatures to design. What I mean by that is, remember in this method how we calculate Q? I have written that earlier. Let me again write it again. How you calculate Q? Q you will be calculated as UA delta T LMTD into FT factor, correct? Do you agree?
Yes, sir.
How you will calculate delta T LMTD? What is delta T LMTD?
Delta T1 minus delta T2 over ln delta T1 by delta T2.
Yes. This is what delta T LMTD is. Now the question is, can you calculate delta T LMTD without knowing the terminal temperatures? So what does it, this methodology requires? You need to know what is the input and output temperatures of both hot and cold fluid. Do you agree? Then and then only you can calculate delta T1 minus delta T2 divided by ln delta T1 by delta T2. What is delta T1? T1 minus T2, isn't it? T1, delta T1 is nothing but what? Temperature difference between hot and cold fluid at location 1, isn't it? Delta T2 is the temperature difference between hot and cold fluid at location 2. Yes or no?
Yes,
so
sir.
you need to know both the terminal temperatures, input and output. Now the question is, as I said, many of you will be working in all these EPC companies where you are going to design the heat exchanger. What I mean by that is you are not having an actual heat exchanger with you. You are designing a heat exchanger. That means you will be only knowing what is the input temperature of the cold fluid and what is the input temperature of the hot fluid. You will not be knowing what is the output temperature. That is what the practically the situation is. Once you have the heat exchanger, you can find out the output temperature. But when your heat exchanger is not at all there, you are designing the entire plant. You don't know what is the output temperature of the heat exchanger, isn't it? Do you agree with me?
Yes, sir.
So how you can design then with this method? Tell me. If you don't know what is the outlet temperature, then how you are going to design? When you don't know the outlet temperature of the heat exchanger, then you assume the outlet temperature, do the calculation and finally match whether you have whatever the assumed temperature you have started with is matching with your actual output temperature or not. So that additional trial and error comes into the picture. So this Kern method is, everything is good, but is applicable only if you know the terminal temperatures. But in a lot of practical applications, these terminal temperatures are not known. These terminal temperatures are not known. You only know your input temperatures. You only know your input hot fluid temperature, input cold fluid temperature. And from that you have to design the heat exchanger. And for this particular aspect, there is another method which is called as effectiveness NTU method. Can you see the point why we are looking at the another method now?
Yes, sir.
Okay, so let's look at effectiveness NTU method. We will cover that and then we will wind up today's class. Okay, is my slides visible to everyone?
Yes, sir.
Okay, so the same discussion is written here. So in a thermal analysis of various types of heat exchangers by LMTD method, an equation is this. Q is given as UAFT delta T LMTD is used. In this equation is simple, but you require all terminal temperatures. And if you are not having all these terminal temperatures, at least you should have a way to determine them easily. Again, so difficulty arises if the temperature of the fluid leaving the exchangers are not known. For example, during the selection of heat exchangers or when the heat exchangers is to be run at the off design conditions, the temperatures of the fluid leaving the heat exchangers are not known, isn't it? So in such cases, even though such cases can also be handled by assuming the terminal temperature, do the calculation, then again go back, find out the outlet temperature and see whether it is matching with the assumed temperature or not. If not, then you go for a several round of iteration and match that. But that requires a trial and error. That requires a tedious trial and error. In such cases, a preferable method is a effectiveness NTU method. So effectiveness NTU method requires only the input temperature. It does not require the outlet temperature for designing the heat exchanger. So effectiveness NTU method, the significance of this method is primarily because of this fact that it only requires the input temperatures. It does not require the output temperature from the heat exchanger. Is it clear to everyone? Does it make sense?
Yes, sir.
Okay. So just bear with me. You will get to know what I'm trying to say here. Okay, so how effectiveness is defined? There are several terms we are defining, but I think you will, gel with whatever I am, discussing. So just pay some attention here. Okay, so effectiveness is defined as actual heat transfer divided by a maximum possible heat transfer. So actual heat transfer is Q. Maximum possible heat transfer you will get when? Maximum heat transfer you will get when you are looking at the temperature difference, which is the maximum temperature difference which can be there in the heat exchanger. What could be the maximum temperature difference in the heat exchanger? Anybody? What could be the maximum temperature difference?
TH1 minus TC1.
TH1 minus TC1. Yes, TH1 minus TC1 will be the maximum temperature difference. Correct. Yes, absolutely. So now this is the one aspect. Second aspect is we can find out the total heat, actual heat transfer taking place between the fluid by calculating the sensible heat, isn't it? So sensible heat lost by the hot fluid is given by what? MH, CPH, THI minus THO. Yes or no? Do you agree? The sensible heat lost by the hot fluid is given by MH, CPH, THI minus THO. So this is nothing but the heat lost by the hot fluid. MH is the mass flow rate of the hot fluid. CPH is the specific heat of the hot fluid. And similarly, this Q will be same as MC, CPC, TCO minus TCI. So this is nothing but the sensible heat gained by the cold fluid. Isn't it? This is the lost by the hot fluid. This is the gained by the cold fluid. So MC here is nothing but the mass flow rate of the cold fluid. CPC is the specific heat of the cold fluid. TCO is the outlet temperature of the cold fluid. TCI is the inlet temperature of the cold fluid. Again, for a simplicity here, MHCPH is denoted by MH only, just CH only, capital C and subscript H. And MCCPC, this entire multiplication is denoted by CC for a simplicity, because this is what these terminologies we are going to use regularly in this discussion. So as I said, Qmax is the maximum heat transfer that can possible in the heat exchanger, that you can get only if the temperature difference you are accounting is the maximum. So maximum temperature difference will be what? THI minus TCI. THI minus TCI. Another physical interpretation of the Qmax is what? Another physical interpretation of the Qmax is if you are using the counter current flow heat exchanger, and if I use a infinite area heat exchanger, that means all the resistances I have removed, isn't it? If I take the infinite area resistance, infinite heat transfer area, All resistances I have eliminated, isn't it? Do you agree with me?
Yes, sir.
If I use a heat transfer area which is infinite, that means I am allowing a infinite amount of time and area to the heat exchanger to exchange the heat between cold and the hot fluid. That means all the resistances I have eliminated in a theoretical point of view. Correct. So in that case, whatever the heat transfer I will get, that is nothing but Qmax. Does it make sense? So that is the thermodynamic limit. In a way, when I am saying Qmax, Qmax is what? Qmax gives me a thermodynamic limit. That is the maximum limit I can achieve. Does it make sense to everyone?
Yes,
Hello?
sir.
Okay, all right. So now in this case, as I said, that maximum heat transfer is possible only if we, if one of the fluid, this is very important. Maximum possible heat transfer would be obtained if one of the fluid undergoes a temperature change equals to the maximum temperature difference present in the heat exchanger. So not both the fluid will undergo the maximum temperature difference, because one fluid will be dominating with respect to the other, isn't it? Correct. Depending on what flow rate I am using. So in this case, which fluid will show a maximum temperature difference which is present in the heat exchanger, it depends on what flow rate and what specific heat a particular fluid is having. And therefore one need to compare this CH value with CC. So the fluid which is having the higher value of CH is not a rate limiting fluid, whereas the other fluid is a rate limiting fluid. Isn't it? So in this case, there are two cases possible. The first case is when CH is greater than CC. So this CH, the specific heat of the hot fluid and its flow rate, this is defined as a CH here. If this CH is greater than CC, that means it has the rate limiting fluid, in this case is a CC. So what happens in such cases? In such cases, the cold fluid, the outlet temperature of the cold fluid actually reaches to the inlet temperature of the hot fluid if I use a infinite length heat exchanger. That's why I have given a break here. This break shows that this heat exchanger is a infinite area heat exchanger. So if I gave a infinite area for heat exchanger, eventually this temperature of this cold fluid, which is starting with the TCI, eventually reach to the inlet temperature of the hot fluid. Because this cold fluid is a rate limiting here. Can you see the point? Does it make sense to you?
So can you repeat the rate limiting part?
Okay. So what I'm saying here is CH is greater than CC. CH is greater than CC means what? CH is greater than CC means what? CH is greater than CC means the hot fluid is having a capacity, more capacity to transfer heat to the cold fluid, and the cold fluid is present in a so see, this CH also accounts the mass flow rate, isn't it? So this cold fluid is having the lower amount present. So eventually what will happen if we give a infinite length heat exchanger, eventually this cold fluid which is entering at a lower temperature TCI, but it will eventually reaches to the highest possible temperature present in the heat exchanger, which is nothing but THI. Isn't it?
Yes, sir.
And why only TCI will reach to THI in this case? Because this CC is smaller than CH. That means the amount of cold fluid is lower than the amount of hot fluid. That means heating the cold fluid is easier compared to cooling the cold fluid, cooling the hot fluid. Yes or no? Does it make sense? That's why this temperature approaches to THI. But there is another case when CH is smaller than CC. That means rate limiting is CH. Hot fluid is a rate limiting case. So in this case, you can see that the temperature, outlet temperature of the hot fluid will be eventually equals to the inlet temperature of the cold fluid, TCI. If I give a infinite length or infinite area. So what it means is, if I give a infinite area heat exchanger, in that case, in that case, it is easy to cool the hot fluid because its CH value is lower. That means its amount is lower compared to the cold fluid. Can you see the point?
Yes, sir.
So eventually THI reaches to the TCI. In both these cases, you can see that in this first case, the temperature difference between the cold fluid is THI minus TCI, isn't it? So the maximum temperature difference is achieved by the cold fluid here. But in the second case, the maximum temperature difference is achieved by a hot fluid. That's what is written here. See, the maximum possible heat transfer would be obtained if one of the fluid undergoes the temperature change equals to maximum temperature difference present in the heat exchanger. Can you see the point? Make
Yes,
sense?
sir. Yes.
Now let's write down the equation. Equation will be what? Qmax will be given by what? Qmax in this case will be given by, if I am looking at only the cold fluid, for a cold fluid, the sensible heat loss will be given by what? The corresponding Cc multiplied by temperature difference, TCO minus TCI. But this TCO is THI. So this will be given by what? Cc is given as THI minus TCI. And this THI minus TCI is nothing but what? The maximum temperature difference present in the heat exchanger, isn't it? So Qmax is given as Cc THI minus TCI. Similarly, in this case, the Qmax I can calculate in terms of the sensible heat of the hot fluid. So that will be given by what? Ch into THI minus THO. Now this THO is given by what? TCI. This outlet temperature of the hot fluid is equal to the inlet temperature of the cold fluid because of infinite length of the heat exchanger. So this THO is replaced by TCI. So this THI minus TCI. So this becomes Qmax is given as CH into THI minus TCI. So overall Qmax is given by what? Overall Qmax is given by Cmin THI minus TCI. Do you agree? Do you agree? Cmin will be the minimum value between CH and Cc. Make sense to everyone?
Yes, yes, sir.
Okay, just a minute. Is my slides visible or I lost?
Visible, sir.
Okay. So that is what we have written here. Qmax is given as Cmin into THI minus TCI, isn't it? Now effectiveness we have already defined, isn't it? Effectiveness is actual heat transfer divided by Qmax. So that we can write effectiveness is given as Q by Qmax. So Q is given as CH THI minus THO divided by Cmin by THI minus TCI, or it can be given as Cc TCO minus TCI divided by. So this denominator will remain the same. Denominator is remain the same, but numerator I can use this as a numerator or this as a numerator, doesn't matter because both are same, isn't it? It's a sensible heat, correct? But if I use a correct value, let's say Cmin is only CH, let's say Cmin is CH. In that case, if I use this as the Q, in that case only the ratio of the temperature difference I can get, isn't it? So in this case, even though I have written this CH by Cmin and this THI minus THO, and in the denominator here THI minus TCI, but let's say if Cmin is CH only, in that case this CH and Cmin will get cancelled out and effectiveness factor will be obtained as the ratio of difference of the temperature. So THI minus THO divided by THI minus TCI. Similarly, in another case when the Cmin is just Cc, in that case this equation we have to use. So when CH is Cmin, then we have to use this ratio. When Cmin is the Cc, then we have to use another equation, because by using this Cc and Cmin both can cancel out. Is it clear to everyone? Make sense? Hello?
Yes, sir.
Again, as we have said that Q by Qmax is epsilon, so that means Q is given by what? E into E, epsilon into Qmax, isn't it? Epsilon into Qmax we can get, and epsilon is what? Epsilon is Cmin into Qmax is what? Cmin into THI minus THI. That's what we have defined here. So Q is given as epsilon Cmin THI minus TCI. So in this equation you can see Unlike the LMTD method, when you are calculating the heat transfer, you are requiring both the terminal temperatures. Here you don't require a terminal temperatures. Here C mean is the specific heat that you can easily get based on the fluid. THI and TCI, these are the input temperatures. That also you can easily get, because whenever you are designing the particular heat exchanger, you already know what is the input temperatures. Isn't it? So everything is known except this epsilon. And this epsilon also you can calculate as a function of UA by C mean and C mean by C max. How these are related with this, that we will see. Is it clear to everyone? So this the physical significance of this equation number 23 is that it does not require you a terminal temperatures. It requires you only the input temperatures. So unlike the LMTD method where you require all input and output temperature to design the heat exchanger, here you require only the input temperatures. Can you see the point? Hello?
Yes, sir.
Now I am saying that the only unknown here is epsilon. And this epsilon we can represent as a function of UA by C mean. And this ratio UA by C mean is called as a NTU. NTU, where U is the overall heat transfer coefficient, A is the area of the heat exchanger, and C mean you already know, the minimum between CC and CH, that is called as a C mean. So UA by C mean is called as a NTU, which is nothing but number of transfer unit. The physical significance of NTU is it gives you the measure of size of the heat exchanger. Higher is the size of heat exchanger, that means more you will be closer to the thermodynamic limit. What is the thermodynamic limit? What is the thermodynamic limit? THI minus TCI. Remember that temperature, maximum temperature difference you can get only if you are having the infinite area heat exchanger. But that is not you are going to have in a practical cases. In practical cases, your heat transfer area is finite, isn't it? So how close you are with that thermodynamic limit, that is governed by this UA by C mean. Does it make sense to everyone? Hello?
Yes, sir.
Okay, again this C mean and C max, this can be calculated because this ratio can be CH by CC if CH is minimum, or this could be CC by CH depending on which value is higher or lower, isn't it? Correct? Yes or no? Does it make
Yes,
sense?
sir.
Now let's look at how to calculate this epsilon. So we will solve only for one case of parallel flow. Only for a parallel flow we will look at. But you can derive the same effectiveness equation. We have derived the effectiveness equation for a parallel flow. Parallel flow is like this. Hot fluid and cold fluid both are flowing in a same direction. But for a counter current flow also you can derive the expression for effectiveness. This equation I have given here, but that derivation you can do it yourself. Okay. So in this case we can define C mean as, let's assume that you can assume C mean as CC or you can assume CH, both. You will get the same expression. But let's start with the C mean as just CC. So epsilon is given by what? CC TCO minus TCI divided by C mean by THI minus TCI. That's what we have written here, isn't it? This is the same equation I am writing. So here this CC TCO minus TCI divided by C mean THI minus TCI. Is my slides visible? Hello?
Yes, sir.
So the same expression we have used, and since we are saying that C mean and CC both are same, so those will get cancelled out. So epsilon will be given by TCO minus TCI divided by THI minus TCI. This ratio of the difference between the temperatures is given as epsilon from the previous equation itself. This is directly coming from this second part. So this CC, we are assuming that the CC which is corresponding to the cold fluid is the minimum. So this C mean and this CC will get cancelled out. So only this ratio will remain. So that's what we are getting here. Now, the sensible heat will be given by MC CPC TCO minus TCI, or this can be given as MS CPH THI minus THO, isn't it? So if I take the MC CPC divided by MS CPH and rearrange this, so that means CC divided by CH if I calculate, isn't it? And since CC is, we are taking it as a C mean, so C mean by C max will be given by what? MC CPC divided by MS CPH. Yes or no? Directly from this equation. This MC CPC we are calling it as a C mean, isn't it? So this C mean, so the remaining will be C max. So this C mean divided by this C max will be nothing but this temperature difference by this temperature difference. Correct? That's what we are getting here. Is it clear?
Yes, sir.
Only 2 slides are there, guys. Please bear with me. We will just extend for 5 minutes, 5-10 minutes, and then we'll wind up. So now, okay, let's calculate Q. Q will be given by what? C mean. This is what C mean is into this temperature difference, isn't it? And this Q is also given by the heat transfer, isn't it? So heat transfer is given by what? UA delta T LMTD. UA, let's assume that the F factor is just 1 here. So UA delta T LMTD we have written here. Correct? So delta T LMTD will be given by what? Delta T2 minus delta T1 divided by ln delta T2 divided by delta T1. Now this equation we can rearrange. Delta T2 is what? So this UA by C mean I can add here, and this ln delta T2 by delta T2 I can take it on the left hand side. So that I have taken here, ln delta T2 by delta T1 I have taken it on the right hand side, and everything I have taken on the left hand side. So this UA by C mean I will have, and this delta T2 minus delta T1 divided by TCO minus TCI we are putting here. So delta T2 is nothing but what? The temperature difference at N2, and this is nothing but the temperature between hot and cold fluid at location 1. So location 2, what is the temperature difference? THO minus TCO, you can see here. This is the location 2, this is location 1. At location 2, temperature difference delta T2 will be what? THO minus TCO. This is THO minus TCO. At location 1, temperature difference is THI minus TCI, THI minus TCI, and subtraction of that this divided by this TCO minus TCI, TCO minus TCI. Now I can rearrange this numerator. So numerator I can rearrange this numerator as TCI minus TCO, TCI minus TCO plus THO minus THI, and this denominator is TCO minus TCI. So this I am flipping. So after flipping I get TCI minus TCO, TCI minus TCO. That's why this minus sign I have taken out here. Now this UA by C mean remain as it is. This TCI minus TCO, this is same. So this becomes 1 plus THI minus THO minus THI divided by TCI minus TCO. So this ratio I am talking about. So this ratio is nothing but C mean by C max. So we can directly write this THO minus THI divided by TCI minus TCO as C mean by C max. So this entire bracket becomes minus UA by C mean in the bracket 1 plus C mean by C max. Is it clear to everyone?
Yes, sir.
And the right hand side remain as it is. So right hand side delta T2 is this THO minus TCO divided by THI minus TCI and logarithm of that. Okay, now let's look at this bracket term which is there in the right hand side. Okay, again this UA by C mean we can represent by NTU because that's what we have defined here, isn't it? UA by C mean is NTU. So we can put this UA by C mean as NTU. So this entire thing becomes minus NTU, and this ln we can take it on the left hand side. So that becomes exponential of minus NTU 1 plus C mean by C max, and the right hand side is just this ratio THO minus TCO divided by THI minus TCI. So now let's analyze this right hand side. So this right hand side is THO minus TCO divided by THI minus TCI. Now I am rearranging this numerator. So I am just putting THI minus TCI minus THI minus THO minus TCO minus TCI. Now if you add this all the terms in the numerator, you ultimately get THO minus TCO. Remember this THI, this first THI will get cancelled out with this THI. This TCI minus TCI will get cancelled out with this TCI, and finally what we will get is THO, this minus minus become plus THO minus TCO. So if I write this numerator like this, it doesn't matter because ultimately their summation is same as whatever we have had earlier. Is it clear to everyone? Hello?
Yes, sir.
Now this I can divide these 3 terms by THI minus TCI. So this THI minus TCI and this is also THI minus TCI, this become 1. Minus THI minus THO divided by THI minus TCO So this THI minus TCO term, this THI minus TCO THO term, this DHI minus THO term, this I can represent using this equation, TCO minus TCI into C min by C max. So this we can put it here, isn't it? C min by C max, TCO minus TCI. And this TCO minus TCI remain as it is. So TCO minus TCI, I can take it common here. So that becomes C min by C max minus 1, isn't it? And if I divide this THI minus TCI, what we get is THI minus TCI is just 1 here. This C min by C max remain as it is. But TCO minus TCI and THI minus TCI, this ratio is nothing but epsilon. You can see from equation 25. So this becomes C min by C max epsilon. And this last term is also minus epsilon. If you rearrange everything, what we get is 1 minus epsilon, 1 plus C min by C max. That's what we get for this temperature difference ratio. Now we can put this entire thing on the right hand side here. And if you rearrange everything, after rearranging, what we get the expression of epsilon, which is nothing but the effectiveness factor of the parallel flow heat exchanger. That comes out to be 1 minus exponential of minus NTU, 1 plus C min by C max, this entire bracket close, and divided by this entire thing divided by 1 plus this 1 plus C min by C max. So this particular value of effectiveness factor is for a parallel flow, but you can derive a similar expression by doing a similar analysis for a counter current flow. For a counter current flow, you get the equation which is shown by equation number 13. That is given as 1 minus exponential of minus NTU, 1 minus C min by C max, bracket close, divided by 1 minus C min by C max exponential minus NTU, 1 minus C min by C max, again bracket close. So this equation 13 is for counter current flow, whereas equation number 29 is for co-current flow. I have not derived expression for 30, expression for counter current flow, but you can derive it. Okay, this is easy to derive. It's not difficult. You start in a similar manner like this, but use a counter current flow. So in a counter current flow, this temperature difference, this delta T is different, isn't it? In a counter current flow, what will be delta T1? What will be delta T1? Anyone?
THI minus TCO.
Yes, correct. Similarly, delta T2, THO minus
TCI.
TCI. Yes, so that difference, if you take it into account and follow the same procedure, you'll get this expression. It's not difficult. Is it clear to everyone?
Yes, sir.
Okay, so this is the last problem of this chapter, and this chapter is done. Monday, we will look at the evaporators. Okay. So a refrigerator is designed to cool 250 kilogram per hour of hot fluid of specific heat 3350 joule per kg per Kelvin at 120 degrees Celsius using a parallel flow arrangement. Again, 1000 kg per hour of cooling water is available for cooling purposes at a temperature of 10 degrees Celsius. If the overall heat transfer coefficient is 1160 watt per meter square Kelvin, and the surface area of the heat exchanger is 0.25 meter square, calculate the outlet temperature of the cooled liquid and water. Also effectiveness of the heat exchanger. So clearly in this particular example, there is no outlet temperatures are given. Yes or no? Outlet temperatures are not given. Only the inlet temperatures are given. Yes or no?
Yes, sir.
Yes,
So
sir.
now which method we have to use? Effectiveness NTU method, because outlet temperatures are not there. Correct. For effectiveness method, first we have to calculate which CC, MCCPC and MHCPH, whether CC is C min or CH is C min, that you have to first determine. So first calculate MCCPC. So mass flow rate is already given. For the cold fluid, mass flow rate is 1000 kg per hour. So kg per hour, so if you divide 3600, that becomes kg per second multiplied by the heat capacity. So for water, the heat capacity is 4186 joule per kg Kelvin. So if I multiply this, I get CC comes out to be 1162.77. Similarly, I can calculate CH. CH is 250 kg per hour multiplied by the specific heat. So 250 into 3350 divided by 3600. So we get 232.63. So now based on this, which one is CC and which one is CH, which one is C min and which one is C max? Hello?
CH is C min.
CH is Cmin, isn't it? So now we can calculate Cmin by Cmax ratio directly. This 232 divided by this ratio we have calculated. NTU also we can calculate. NTU is what? UA by Cmin. Cmin we already know, this CH is a Cmin. And U is already given. U is given as 1160. Area is also given. So UA by Cmin we have calculated. Since the example is using a parallel flow heat exchanger, that means we have to use this expression. This is the parallel flow heat exchanger equation. In this equation, the only parameters are NTU and Cmin by Cmax. So Cmin by Cmax we have calculated. NTU also we can calculate it. We put both the values here. We can calculate the effectiveness factor. Effectiveness factor comes out to be 0.646. Once we know the effectiveness factor multiplied by Qmax gives me the actual rate of heat transfer, isn't it? So Qmax we know. Qmax is what? Cmin into the maximum temperature difference. What is the maximum temperature difference? THI minus TCI. So THI minus TCI multiplied by this Cmin gives me the Qmax. Qmax is 25,589.3 watt. And if I multiply this Qmax to this effectiveness factor, that gives me the actual Q. So actual Q comes out to be 16,530.6 watt, isn't it? Once I know the actual Q, I can use the equation for the sensible heat and I can calculate the outlet temperature. So Q is given as Cc, TCO minus TCI. Cc we already know, Cc is this. We can put all the values and we can calculate TCO. TCO comes out to be 24.22 degrees Celsius. So outlet temperature of the cold fluid, outlet temperature of the water will be 24.22 degrees Celsius. The inlet is 10 degrees Celsius. Similarly, the outlet temperature of the hot fluid also we can calculate. So sensible heat also given by CH, THI minus THO, isn't it? If I rearrange that, I can get THO. THO can be obtained as THI minus Q by Cc, isn't it? This directly obtained from this equation. So Q is given as CH, THI minus THO. We can rearrange this to obtain this equation. Yes or no? Correct? Yes or no?
Yes,
So
sir.
with this, yes, please go ahead. Is there any question? Hello?
No, sir.
So with this equation, we can obtain the outlet temperature of the hot fluid. So outlet temperature of the hot fluid comes out to be 48.94. We started the hot fluid temperature of 120, but the outlet is, it cooled down to a 48.94 degrees Celsius. So is it clear? Everything is clear to everyone? Whatever we have discussed today? Hello?
Yes,
Yes,
sir.
sir.
Okay, so this is the last slide of this heat exchanger design. Several problems are solved in the book. Okay, again I am saying in the quiz tomorrow, we are having a quiz tomorrow from 9:30 to 10:30, LH 121. You all have to bring your scientific calculator with you. Only the BK Datta book is allowed and the printout of these PPTs are allowed. Don't bring anything else than that. Okay. If you do not have a book with you, at least you bring the printout of these PPTs. These PPTs are self-sufficient, as I said. But book, because in the book several problems are solved, many other things are there, so that gives a comprehensive picture. Okay, that's why I'm asking all of you to purchase a book. Book is not costlier. That is only 350 rupees on Amazon. You can purchase it. It costs you less than a pizza. Okay. Is it clear to everyone? Hello?
Yes, sir.
And again, I am apologizing all the students to, take this lecture on Saturday. I know it's painful to, come on Saturday, but we have to complete the syllabus as early as possible. So I probably will require only 2 lectures. So Monday lecture, and after that we will get one more lecture on Thursday. So by that we will complete the entire syllabus. Okay. So tomorrow 9:30 to 10:30 LH 121 we will have a quiz. Please go through the material carefully. The syllabus is up to whatever we have covered till 14th of March. 14th of the March. Okay. Is there any question? Is there any question, any comment? Hello?
No, sir.
And thank you for attending. I think only 3-4 students have attended. I am really sorry, but I hope it is okay. Please don't mind. Okay. Is it okay? I mean, recording is available. All right. Sorry. Let's stop here and see you tomorrow personally.